So, today we are going to deal with second order difference equations with constant coefficients and constant term. So basically, we are dealing with equation of this form, yt plus 2 plus plus a1 yt plus 1 plus a2 yt plus c. And look, we already have a lot of experience dealing with differential equations, and we will use the same approach to solving it as in the previous cases. So first, we're going to start with particular solution. So the equilibrium value. We need to try first the easiest possible solution, well, which is simply constant. So yt is equal to some constant. Now look, if yt is equal to some constant, then yt plus 1 as well as yt plus 2 must also be equal to some constant. So now that we've established that, we can just simply substitute this into the equation. So we get that this is k plus a1, k plus a2, k equals to c. We can factor out k, and then we obtain that k is equal to c over 1 plus a1 plus a2. And right away, we can impose here a restriction that a1 plus a2 must definitely be different than -1, otherwise the solution collapses. So we get that particular integral, a particular solution here is given by a constant c over 1 plus a1 plus a2, keeping in mind that the denominator must be different than 0. Okay, let's try an example. We've got that yt plus 2 minus yt plus 1 plus 4yt is equal to 6. Okay. We are looking just for equilibrium values, so we are looking just for the particular solution. But let's try if we can. So let's try the solution. So all we've got to do is to substitute all the coefficients and the term into the formula here. We've got that this is 6, 1, minus 3, plus 4, which gives us 6 over 2, or simply 3. As you can see, this is not very complicated. But now, what if it happens that a1 plus a2 is equal to -1? Well, in this case, we can no longer use this solution. Our solution collapses, and we need to try something different. So, what should we try? Well, of course, the second easiest solution we can try is a linear solution. But in this case, yt plus 1 is equal to kt plus 1, and yt plus 2 is equal to kt plus 2. Now, what do we do is that we substitute all those into the equation, and we get that this is kt plus 2 plus a1 kt plus 1 plus a2 kt equals to c. And look, we can right away notice that all of these expressions have k. So maybe let's factor out k, and Well, now we just need to multiply everything out inside the brackets. But look, we can notice another thing. T here appears 3 times. So let's put all expressions next to T in parentheses. And we get out of this that this is 1 plus A1 plus A2 T. And now we have plus A1 plus 2. But look, this expression reminds us of the denominator in the particular solution in the previous case. Well, under our assumptions, it needs to be equal to 0, because A1 plus A2 is equal to -1. So this part disappears. All we've got left inside the brackets is A1 plus A2. If we divide both sides by this expression, we get that K is equal to C over A1 plus 2. But now we need to add a second provision that A1 must be different than -2. Okay, so knowing this, we can write that particular solution in the case of A1 plus A2 equal to -1 is simply equal to C over A1 plus 2T. Remembering that A1 cannot be equal to -2. Okay, let's make an example for this case. So we've got that YT plus 2 plus YT plus 1 minus 2 YT equals to 12. Well, let's first look at the coefficients. We see that the coefficient A1 is 1, A2 is -2, their sum is equal to -1. So we should use this formula. Okay, so let's do it. We get that this is 12 over 1 plus 2 T. So this is simply 4T. Okay, so now what happens if we have a situation where not only A1 plus A2 are equal to -1, but also A1 is equal exactly to 2. -2, I'm sorry. Well, look, first let's notice that this is a very specific case and concerns only one difference equation. So this is a difference equation, well, of course, assuming actually infinite number, but they all are different only with respect to C. So we would have difference equation in the form now the question is, have we seen it somewhere? Well, a couple of videos ago when we were dealing with methods of undetermined coefficients, this expression appeared. And look, this is nothing more than the expression that we obtain if we take first difference of YT and then we will take the first difference of the first difference. So look, here we've got expression when the second difference is equal to a constant. So we have a constant growth. But about this, not constant growth, but constant acceleration. But about it a little bit later. So, how do we solve equation like this? Well, again, first and second option will collapse. We need to try the third trial solution. The third easiest function Well, it's quadratic function. But in this case, we will have yt plus 1 equal to kt plus 1 square, and yt plus 2 equal to kt plus 2 square. Okay, now we substitute those into the equation. So we've got that this is kt plus 2 square plus a1 kt plus 1 square plus a2 kt square. Okay, and this is equal to c. Look, again, we see that all expressions share a common factor k, so let's take it out. And now, let's calculate everything we've got inside. So we've got t squared plus 4t plus 4 plus a1t squared plus 2a1 plus a1 and finally plus a2t squared equals to c. Let's do the same thing we've done previously, which is let's collect all the expressions, now this time with t squared together and then with t together. So we've got that this is k, 1 plus a1 plus a2 t squared. Then we've got 4t and 2a1 so 4 and oh, I'm sorry, I'm missing t over here. Yeah, so plus 2a1t, and now we've dealt with this, with this, with this, with this, with this. We've got a1 plus 4. Yep, and here we put just parentheses. Okay, so now let's see what we're going to have over here. First, under our assumptions, this is equal to 0. This expression is gone. Under our assumptions, also 2 times a1, which is negative 2, gives us negative 4. This is 0, so this expression is gone. And now look, here we have 4 and a1. a1 is negative 2, which gives us just 2. So, out of this, we can easily calculate that k is equal to c over 2, and the particular integral that a particular solution we wanted to find is c over 2t squared. Okay, so let me check how much time do we have left. Okay, so basically these are all the 3 expressions for a particular solution that you can get in this case. So now that we've got particular solution, maybe let's move to the complementary function. Just as before, complementary function is telling us what do we need to do, what will happen if a variable is thrown out of the equilibrium. But with our experience from before, we know that in order to obtain complementary function, we don't need to solve the entire equation. We just need to solve homogeneous equation. So at this moment, what we can do is that we can drop the constant c and replace it with 0. Now, but what solution should we try? Well, we have some experience from differential equations when we had expression a times e to the power of t. Here it's not going to work just as fine as before, but there is a very similar option that we are going to try. And our trial solution is going to be yt equals to ab to the power of t. Looks very similar, but of course we don't have e to some power, but we've got b over here. Why? Well, we remember from our experience with first order difference equations that in this case we need to have, we can have negative values in place of b. So e to the power of something doesn't work. So look, combining our knowledge about second differential equations and first order difference equations, we can clearly see that this would be the best option. Okay, so let's substitute the trial solution over here. We get that this is a b t plus 2, right? Plus a b t, I'm sorry, a1 a b t plus 1 plus a2 a b t equals to 0. Look, now we can take the common part out, and the common part out being a b t, and what we've got left there is b squared, right, plus a1b plus a2 equals to 0. Now look, this part cannot be equal to 0, so what we are left with is the characteristic equation that we've been dealing before. Then, the characteristic equation, of course, we need to deal with is b squared plus a1 b plus a2 equals to 0. Look, again, we arrived at exactly the same situation we've been dealing with when we were dealing with second order differential equations. So what do we need to do next? We need to find characteristic roots. And of course, our characteristic roots are given by minus a1 plus minus 4a a1 squared minus 4a2 over 2. In general, of course. But as I hope you remember from our experience with second order differential equations, when we arrive at this point, we can encounter 3 different cases. Each of these cases, of course, pertains to the different value that we can have under the root over here. If it's positive, we will have distinct roots. If it's equal to 0, we will have repeated roots. If we have negative value, then of course we will have complex roots. Well, if time permits us, we will do the repeated roots, at least distinct roots, in this video, and we deal with the rest in the next one. Okay, so let's start with distinct roots. So now we are dealing with the case when a1 squared minus 4a2 is bigger than 0, so a1 squared is bigger than 4a2. Look, what will be our solution? Well, here complementary function is simply 1 b1 to the power of t plus a2 b2 to the power of t. As you see, the case is extremely similar to what we've seen in the case of differential equations. Okay, let's try with an example. Okay, let's do equation we already did before. So yt plus 2 plus yt plus 1 minus 2yt equals to 12. Look, in this case, we've already, and we have two initial conditions, y0 equals 4 and y1 equals 5. Okay, in this case, we've already calculated particular integral. This is particular integral is equal to 4t, so this is a moving equilibrium. So now let's move to finding a complementary function. So in this case, we see that a1 squared is equal to 1, which is clearly bigger than negative 8 equal to 4a2. So we can just substitute everything to the formula. Okay, so we will obtain two distinct roots. So we have negative 1 plus minus square root of 9 over 2. So we have first negative 2 over, I'm sorry, we've got 3 minus 1. First we have 2 over 2, and then we have the second one will be negative 4 over 2, negative 2, or simply we have now 1 and negative 2 as our roots. Okay, so basically, in this case, the complementary function is given as a1 times 1 to the power of t, but 1 to the power of t, this is simply 1, right? So let's keep it like this, plus a2 times negative 2 to the power of t, and that's it. Now, so the full solution, the complete solution to the equation, but in general form, is then given by the sum of complementary function in particular solution. So it's a1 plus a2 minus u times negative 2 to the power of t. I think that was plus 4t. Okay, now in order to obtain definite solution, we need to use initial conditions. Our initial conditions are y0 equals 4, y0. We substitute 0, we get a1 plus a2 equals to 4, right? 0 over here, this turns into 1, this turns into 0. Then we've got that y1, we've got again a1 minus 2a2 plus 4, but is equal to 5, right? So if we move 4 to the other hand side of the equation, it will be equal to 1. So what we need to do in order to solve this equation is to solve a very simple system of two simultaneous equations for a1 and a2. So the determinant here is negative 3. A1, if I take 4 and 1 over here, we got that this is negative 8 minus 1. It's negative 9. A2, if I put 4 and 1 over here, this is 1 minus 4. It's negative 3. So we get that A1 is equal to 3 and A2 is equal to 1. So consequently, our solution is given by 3 plus negative 2 to the power of t plus 4t. Okay, and I don't think we have enough time to do repeated case right now, so we're going to deal with this in the next video. Thank you for your attention.